So I want to shift gears, and I want to tell you that, of course, we use this for research, and I'm going to give you a couple of examples, very simple ones today, where we actually how we use them in the research and how quickly we can actually develop something um, and prove out things to ourselves. So the first one is a proportional resonant controller for a LCL-based grid-tied inverter, and the second example is for a PV applications cascaded converters. So this was this work actually resulted in a paper that we presented in 2014 at the ECCE, and again, what I'm trying to show you is that these kind of systems enable the students to not only design the controller and have a validation, but ask what-if questions. So that point is very important in my mind for the students to actually push the corner points, and also they understand the limits of both the converter as well as the controller. So again, here's a very, very simple system where we have an inverter which is grid tied with LCL filters to the grid. Now, a very simple system for all power electronics folks, right? We build these converters in our lab. We have done n number of work with these kind of things. But we still have questions, questions in the sense that, okay, what happens if the grid behaves in a certain manner? What happens to my converter? How should I design my filters? How should I design my controllers? What should be the values of my filter values? What should be the converter values? How should I design my DC bus? All those kind of things. What should be the cutoff frequency of my controllers? What should be the switching frequency? All of those things come into our mind, right? And we start off with some design, and then we try to validate in the lab. But then the problem is that in the lab, we can't, we are stuck with one particular design. And in terms of our converter, in terms of our structures, in terms of our values and specs of the components, passive components. So here I'm just walking you through the modeling of our controller. And again, these are things that, folks, we know in power electronics research. So we know how LCL filter-based converter system is an undamped system. We can passively damp it with control loops, and we can actively damp it with different kinds of control loops. And again, what we are looking for from a very simple research questions is that we have, so going from here to here is pretty easy in terms of going from undamped to passively damped system, but then going from here to the active damping part of it, we have a few different ways of doing it, and we want to very quickly come to a conclusion of pros and cons. And as a starting research student, I want to understand the impact of the delays, impact of my sensing, bandwidth of my sensors, bandwidth of my controller, and how these different choices that I can have or control loops that I can have out here will play out. And that's what this rapid prototyping provides us. So obviously, in electrical engineering, always we start off with a Bohr diagram, and we try to understand, where the problem space is in terms of frequency, and then we try to play around with our controllers. So we again walking through the different types of controllers that we traditionally play around with, PI, the PR resonant controllers, and embedded with damping. And again, because we are in this rapid prototyping mode, we now can actually start playing around with these parameters, not only in simulation, but actually with as if a hardware system with a real controller. So here's a control schematic of taking our grid voltages from ABC or the inverter output voltages and currents, and going through a DQ transformation to help us in our control, and implementing the control in terms of the PR controller that we just talked about with active damping. Right? So as I said, in this case, we again went to a HIL 402 system where we emulate this entire system that you see out here with the converter, the LCL filters, the grid, and now we can actually interface a real controller. And in this case, we have a TI DSP 335, as it's typically called, board, which connects very easily to the HIL system, with the Typhoon HIL system. So again, we have outputs of in terms of analog signals of the current voltages, and we can display whatever we want on the scope. So so here are some results. Again, these are representative results showing you how it is done, how easy it is. So in the controller hardware in the loop, so there is the hardware of the converter, and the filter is in the HIL. The controller is outside, and the current control is implemented with this PR controller. And again, we see grid voltages and currents. And as we vary the frequencies, what kind of impact do we have? What kind of harmonics do we have? So now you've seen that how easy it is and how quickly can we get these results. A research student, even a starting research student, in the first year of their master's PhD, can actually sit down and do this thing in a matter of a couple of days. And this is the point where they start actually looking at all the corner cases. Okay, what happens if I design my controller differently? And you instantly get validation of it. So again, different kinds of controllers, and I can actually set up whatever metrics I want in terms of comparing them. So this is just an example where we're looking at the harmonics at different frequencies with different types of controllers for. So we can go back, and now where this thing becomes very useful is that I can go to any particular standard or code and see what kind of disturbances the grid will go through, or what is allowable from the grid side. And I have to make sure that under all cases the controller meets certain performance metrics. And again, you can run those through cases, and you can even write a script actually to do this thing like a batch file. So things have become so easy from that point of view. And what this enables a research student to do is to think actually deeper and to go to the next level. So this was one very simple project, and it's instant gratification for students, because this is an example where a research student can go through this kind of analysis and come out even with a paper. So again, another example is PV, and of course, as everybody knows, there's lots and lots of work going on PV, and we need more and more research and to make PV as inexpensive as possible. And so we're looking at different kinds of configurations for PV systems all the time, and where we're looking at parallel converters or cascaded converters. We're comparing them. We always want to make it cheaper while not giving up anything on the efficiency part of it. In fact, make it higher efficient. And there are lots of other concerns. We want it to be safe. We don't want leakage currents. and we don't want to have arc voltages and all kinds of things. So here's a very quick example where, again, a very simple example where we have cascaded, three converters, very simple, where we have PV sources, and we want to cascade them up such that we get a higher voltage, and then we can connect it back to the grid or supply our loads. And now we have a method. So basically all that we have is three voltage sources in series, and we have a method of actually building up our voltages the way we want it. So here's an example where we looked at, how should we control each of these things. If one doesn't know that the other exists, then basically, we control them as non-interleaved systems, and there are some bad things that happen with the non-interleaved systems. And if we know that we have n number of these and they can be controlled as a system, then we can interleave them and and get better waveform quality on our DC bus. So that was kind of the exercise that we were trying to do. And here's examples of different PV parameters with the three bridges and output voltages that we wanted out, and very simple design parameters. Now again, with the HIL system, you can play around with these design parameters very quickly and optimize them. So here's examples of non-interleaved systems where we have the output voltages and the DC bus voltage ripple being high, and with different kinds of fixed interleaving where we reduce the DC bus variation, and then with a variable interleaving where again all we are trying to optimize is the variation of this thing of the DC bus such that we can reduce our leakage currents. Yeah. So my point again is that all these kind of what if scenarios, different controllers, different algorithms can be very, very easily tried without the fear of anything blowing up. And I think that's a very important thing because we spend 80% of our time, if we had to build the hardware, in actually building the hardware, and the job doesn't end there. The job then becomes that how do I make sure that I protect my hardware when I'm playing around with my controller, and if I do something wrong with my controller, my hardware blows up. So then again I spend 80% of my time making sure that my hardware is up and running before I can do anything meaningful. So we have taken away all that time, and so that's why I say that we are now empowering students to actually do the thinking and the work that we really want them to do. Their contribution is actually coming up with new things and to compare things such that things can be made cheaper, more efficient, and so on. So again, the proof is that we can actually implement these things. We implemented this thing with a HIL 402. We have a controller here, and again, the students can play around with this, look at their metrics, in this case the DC bus voltage variation, and instantly see what their algorithms would give us. So I think I want to make sure that I at least convey the point that this has become such an integral way of our thinking now that we think that there is this is enabling so much more in terms of doing the real work, which is coming up with new things, coming up with new controllers. And in power electronics, the whole reason why we're doing power electronics is to gain efficiency and driving down the cost at the same time.
Great. Well, Professor Bhattacharya, this is phenomenal. This is really impressive spectrum of examples and applications. It's really amazing. Quick question. Tell us when did you start working with real-time simulation and hardware in the loop? When was your first exposure in your long career, both as an industry leader as well as a professor?
So that takes me back to my University of Wisconsin-Madison days. When I joined as a grad student, actually, at that time in the 90s, there was no real-time simulator. And one of the projects that I first worked on was actually building up a real-time simulator. And at that time, we were doing with Texas Instrument DSPs, and we physically built, DSP cards which could run simple buck converters, boost converters, resonant converters in real time. And real time at that time was 5 kilohertz PWM, 10 kilohertz PWM at the max. That was kind of the limit with the DSPs that we had. And we had to do a lot of things. I mean, FPGAs were not there, and we had to physically program the differential equations into different processes and do all that algebra and all the things ourselves. I think moving on to so we realized the importance of it, and then I can tell you that in my days when I worked with Westinghouse in the facts area, um, the our group was the pioneer of actually coming up with the flexible AC transmission system, and our group built converters which were 100 megawatt, 150 megawatt for transmission applications. And our customers were utilities. And as you can imagine, these projects were big, both in terms of money as well as in time. So a project could run, 2 years to 5 years and could cost anywhere between $20 million to $50 million. And so if the utility is spending that kind of money, they do not believe in simulations. They need to see some hardware proof that what they're buying and what they're investing. And at that time, we still did not have real-time simulators, and so we actually built up simulators in analog digital fashion. And controller hardware in the loop was done because that is how we developed our controls. That is how we showed the customer or the utility what these devices would do in their system. And we went through all the fault cases. And where it actually helped us a lot is that when we were commissioning these kind of big utility converters, we would see a lot of things on the grid that we could not explain. And so instead of playing around on the real system, because things might blow up, we came back to our simulators, and we would recreate the grid scenarios that we would have seen, and then try to actually develop controllers that would take care of or let us operate in those conditions. So I think we are back to the same exact kind of scenario out here, is that if you are deploying something in the field, like a UPS system or a microgrid, and you can't predict everything that you would see in the field. You can't predict all the fault modes. And so it will pay to actually have a simulation or emulation, hardware in the loop kind of a system where you could fall back during your commissioning of the real system such that, you make sure that all your controllers work. And that's an invaluable thing.
That's phenomenal. So basically, in your career, you have witnessed this transition early on. Industry had to basically build their own hardware in the loop real-time simulators in order to be able to test and validate the controllers and converters and all different system configurations. And now these days, I guess we're seeing somewhat of a shift to an off-the-shelf hardware in the loop solutions where industry and academia doesn't really have to rely on their own in-house systems. What are your thoughts on the industry's adoption rate of hardware-in-the-loop testing? Do you have the feeling that this transition when it comes to power electronics industry is a little bit slow? I mean, transitioning from kind of like in-house, full power testing, and some of the industrial leaders actually building their own in-house solutions. That switch to off-the-shelf solutions that are available. Do you have a feeling that, or what are your expectations in terms of when do you expect this transition to happen? How do you see this whole process?
So I think from my experience, from my industry experience, I think the education component is very important. I mean, folks in industry, are extremely busy, and therefore, the education component through webinars like this, I feel becomes an integral part, or should become an integral part, because industry sometimes, more often, doesn't have the time to actually do the research part of actually going through all the steps and coming to these kind of conclusions as I'm showing, where we are trying to use it for teaching, research, and so on. But I think hardware in the loop and controller hardware in the loop is getting very well established, and I think the education component is very important, such that a wide adoption happens in industry. I mean, this is a thing that's not limited, you know, um, to one sector of the power electronics industry or the other. This is a broad thing, and if you look at it, it has happened already in other industrial sectors. Like, for example, as you said, flight simulator. I mean, aerospace industry, automotive industry, they are well versed in hardware in the loop simulators, and I think in power electronics we should be.